I wanted to do a real quick review of Chapter 4. So I'm going to run through the Unit 4 summary. It's at the very end of the chapter. As I do, I'm going to go back and go through a couple of examples from 4.6, which is the review assignment. So the very first thing we went through is approximating using tangent lines. So if you remember, we find the tangent line at a convenient point. So the convenient point is usually one like with whole numbers, an easy one to plug in. So we find the tangent line, and then we plug in the x value that we're trying to find, or trying to approximate into the tangent line, and it'll give us an approximate of the y value on the curve itself. So a quick example of that. Number 1 and 2 are both good examples of using the tangent line to approximate a value. So I think with you, I'm just going to go through and do number 1. So it says y equals x over x plus 5. Find the equation of the tangent line when x equals -6, and use it to approximate the y coordinate when x is equal to -6 1/5. So this is what we're trying to approximate, is what is the y when x is -6 1/5. Well, that's hard to plug in. So instead, I'm going to use this point right here. So the x equals -6. We're going to plug that in and find the equation of the tangent line. So to find the equation of the tangent line, I need a point and the slope, right? Here's my formula. Y minus y1 equals m times x minus x1. So let's find a point first. If I plug -6 into there, y of -6, I would get -6 over -6 plus 5, which is -1. So it comes out to be a +6. So my point is -6, 6. So I've got y minus 6 equals whatever my slope is times x plus 6. Okay, to figure out my slope, I've got to find the derivative. So let's find the derivative. I've got to do the quotient rule. So I take the bottom times the derivative of the top, which would be 1, minus the top times the derivative of the bottom. So that's x times the derivative of the bottom would also just be 1, all over x plus 5 squared. So up on top, end up with x minus x. So the derivative ends up being 5 over x plus 5 squared. Now I want to plug -6 in there to find the slope. So if I plug in -6 on the bottom, I get -6 plus 5 is -1. Squared is 1. 5 divided by 1 is 5. So I end up with 5 as my slope. So there's the equation of my tangent line. We've done that a lot before. Now what I'm using it for is to approximate the y when x is -6 1/5. So plug in -6 1/5 right there for x. So y minus 6 equals 5 times -6 1/5 plus 6. Hey, -6 1/5 plus 6 is a -1/5. -1/5 times 5 is a -1. Add the 6 over. So we end up getting, sorry, I'm jumping all over, but we end up with y minus 6 equals a -1. Add the 6 over, so we get 5. So up here, I would say, when x is -6 1/5, y is approximately 5. That's what it comes out to be. So that's approximating using the tangent line. Make sure you remember that's also called local linearization. That's the other way we refer to that. Okay, so number 2 is similar to that. The difference is it already gives you the point. The point's 4, 3, and it already gives you the derivative, the slope. So we don't have to actually find all that like we did on number 1. So go back and review that. You'll have some questions that have to do with that on there. Okay, next thing we did was L'Hopital's rule. So remember what L'Hopital's rule said is if you go to take a derivative and you try direct substitution, and you end up with either 0 over 0 or infinity over infinity, that includes plus or minus infinity over plus or minus infinity. When you do that, then you can take the derivative of the top and the bottom and try again. And you can keep doing that as many times as you want, as long as you get 0 over 0 or infinity over infinity. And the idea is that eventually, as we take the derivative, that we'll end up with something that when we try direct substitution, that direct substitution now works. So there's a section on this review. There'll be a section on the test where you're practicing finding limits. Some of those L'Hopital's rule apply, and some of them they don't. So let's take a look at a couple of those. So the section on the review is 4 through 9. So let's actually just do number 4. 4 is a good example. If I plug in pi over 2, sine of pi over 2 is up here. The sine is your y coordinate, which is 1. So sine of pi over 2 is 1. So I end up with 2 minus 2 on top, which is 0. If I plug pi over 2 in the bottom, I also get 0. So L'Hopital's rule applies here. So let's take the derivative of the top and the bottom. So I'm going to say the limit as theta approaches pi over 2 of derivative of 2 is 0. Then I have negative 2 times derivative of the sine of theta, which is cosine of theta. Then on the bottom, the derivative of theta is 1, and pi over 2 goes away. So I end up with that. Plug in pi over 2 again. Well, the cosine of pi over 2 is 0. Negative 2 times 0 is 0, so my answer comes out to be 0. All right, so as long as you get 0 over 0, or infinity over infinity, then you can apply L'Hopital's rule. Make sure that's the case. So like on this number 5, you're not going to get 0 over 0. So this would not be a L'Hopital's rule. Just do direct substitution and it works. Also be aware, something like number 8, if you have a polynomial on the top and the bottom, and as x goes to infinity, the top goes to infinity and the bottom goes to infinity, you could apply L'Hopital's rule. You'd have to do it a bunch of times before it would work. But you can also use the other stuff we know. If it's going to infinity, it's end behavior. So we can just compare the leading terms. They're both x to the fourth. It's 5 over 1. So sometimes it's easier not to use L'Hopital's rule, or sometimes L'Hopital's rule doesn't apply. So you want to be careful with that. That's something to keep in mind as you work on those limits. So that was the second. That was 4.2. That was the second lesson we went through. After that, we did absolute extrema. So just remember, we do that candidate test. And the way the candidate test works is you find all the critical numbers. Remember, critical numbers are when the first derivative is undefined, or when the first derivative is equal to 0. So you take the derivative, you look at when it's undefined or equal to 0, and that gives you the critical numbers. Once you have the critical numbers, you take the endpoints and the critical numbers, and you find all of the y values. And after you're done, the one with the highest y value, the largest y value is your max. The one with the smallest, the lowest y value is your minimum. Be careful with this. We don't want to confuse this with relative max or relative mins. On those, you do the number line test. But on an absolute max, absolute min, you don't. So let's do an example of that. So there's a couple of those, again, on the review assignment. 11 and 12 are both absolute maxes or absolute mins. Let's pick one of those, and we'll kind of run through it here together so you can see an example. Let's just do number 11 up there. Actually, let's do 12. So let's find the absolute extrema for g of x equals 3 halves x to the 2/3 minus x on the interval from -8 to 1. So start out by finding the derivative. We need to find our critical numbers. So if the 2/3 drops down, 2/3 times 3 halves is 1. So I have x to the -1/3. Got to subtract 1 from the top. Minus derivative of x is 1. Okay, I got to find out when that's undefined or when it's equal to 0. As a quick side note, I'm going to write it this way. That's the same thing as saying the cube root of x, right? X to the -1/3 minus 1. So when is it undefined? Well, if I put a 0 in, I get a 0 on the bottom of the fraction. So at 0, it's undefined. So one of my critical numbers is that x equals 0. Sorry, I can't write x's. I also have to find out when it's equal to 0. So let's do that. So if I go 0 equals 1 over the cube root of x minus 1. If I add the 1 over, you could actually cross multiply or times by the cube root of x. Anyway, we end up with the cube root of x equals 1. Cube both sides, so x is equal to 1. Okay, so those are my critical numbers. Now all I do is make a list. I find all my y values. So all I do is take g of -8. That's my endpoint. G of 0, G of 1, and G of, actually, that 1 ends up being the endpoint also, right? So I don't have to do that. Just have those. Okay, plug those in there. So if I plug in a -8, now when I plug it in, I'm finding the y values. So this is important. We're not plugging in the derivative, you're plugging in the original function. So that'd be 3 halves. I'm going to rewrite that just to make it easier. That 3 halves x to the 2/3. I'm going to write it as being 3 halves cubed root of x squared. This is a cube root of x squared minus x. So if I plug negative 8 in there, I get negative 8 squared is 64. Cube root of 64 is 4. 4 times 3 halves is 6. Minus, and plug your negative 8 in there. So I'm going to end up with 14. 0 is easy. If I plug in 0, I get 0 for both of them. If I plug in 1, this would just be 1 times 3 halves is 3 halves. Minus 1. So that's going to be a half. Okay, so just look for your max value. Your largest y value is 14. That's when x is negative 8. And your smallest y value is a half. That's when x is 1. Now, if it says find the absolute extrema, it wants the y values. The absolute max or minimum is the y value. So we'd say the absolute maximum is 14. The absolute minimum, did I say a half? Sorry, the smallest or the lowest gets is 0. So the absolute minimum would be 0. So absolute max of 14, absolute min of 0 on there. Okay, so make sure you review over that. You can look at that section 4.3, finding absolute maximums and absolute minimums. Okay, the next thing we did, and I'm going to kind of do these together, is we found relative extrema. And there's two ways to do that. Relative extrema, remember, mean relative minimums, relative maximums. The way we normally do it is the first derivative number line test, where you find your critical numbers, put them on the first derivative number line, include domain restrictions, okay? And then you just test the intervals to see if they're increasing or decreasing. We had that second way, the second derivative test, where you found your critical numbers, and then you plug them into the second derivative to find out if they were concave up or down, to see if they're maximum or minimums. Don't do that unless you're asked to. So mainly we're going to do the first derivative test, number line test. If you want to find concavity, it's just like, or it's parallel to the process we do when we find the first derivative, when we find the increasing, decreasing, and relative mins and maxes, except we do it with the second derivative. So you take your second derivative, find your possible points of inflection. That's when the second derivative is 0 or undefined. And we make a second derivative number line. And then make sure you put your domain restrictions on there. And then again, we just test the intervals to see if it's concave up or concave down. All right, let's look at an example of that. If you look at numbers 16 and I think it's 16 and 17, they actually ask you to do both, find the relative mins and maxes and the relative extrema. Actually, it's just 16 that they have two different functions for 16. So let's just pick one of those, and we'll go through the process for both. We'll find the relative extrema and the points of inflection. So let's do 16a. So let's start with the first derivative. So y primed equals 3x squared minus 6x minus 9. Let's just find the second derivative while we're at it. So that would be 6x minus 6. Okay, now let's do our number lines for both. Oh, I'm sorry, at the very beginning, check for domain restrictions. So is there anything that x cannot equal up there? This one's a polynomial, so there's no domain restrictions. X can be anything. Okay, go down to our derivative. Is there any time when the first derivative is undefined? Well, f prime is always defined. So there's no critical numbers there. So the next thing is, when does the first derivative equal 0? That's what we're going to do next. So let's take that and set it equal to 0. So I'm going to go 0 equals 3x squared minus 6x minus 9. I can divide all those by 3. It'd be x squared minus 2x minus 3. That factors x minus 3, x plus 1. So x equals 3. And x equals negative 1. Okay, that's what I'm going to put on my number line for f prime. So here's my f prime number line. I put negative 1, positive 3. When you test your intervals, you're testing the slope. You want to find out if the slope is increasing or decreasing. So we're going to use our derivative right here. So I'm going to pick a number to the left of negative 1. We can do negative 2. Negative 2 squared is 4, times 3 is 12. Negative 6 times negative 2 would be a positive 12. It's going to be a positive. Pick something between negative 1 and 3. You could do 0. That'd be 0, 0 minus 9. It's a negative. Pick something to the right. We do 4. That would be 16 times 3 is 48, minus 24, minus 9 is going to be a positive. Okay, so find all the x values of the local extrema. So the x values, we'd say there is So this is going from increasing slope to decreasing slope. So there's a max at -1. Then it goes from decreasing slope to increasing slope at 3. So let's put that down first. There is, I'll write it over here, there's a relative max at x equals -1. And there's a relative min at x equals 3. Make sure you're careful and read the directions. On that one, it only asked for the x values. If it asked for the points of the local extrema, then we'd have to plug the -1 and 3 back into your original function to find the y values. Okay, there's the first half. That is the first derivative number line test. It's finding when functions are increasing or decreasing. It's finding when you have local extrema. The second part is finding points of inflection and concavity. So that's the second derivative. So we do the same thing, but we just do it with the second derivative now. So find out when it's undefined or equal to 0. It's never undefined, but it does equal 0. If I factor a 6 out, right, it'd be equal 0 at 1. So my possible points of inflection are at x equals 1. Put those on the second derivative number line. So that would be at 1. Test some points on either side. And when we're testing them, we're checking concavity, so we're plugging it again in the second derivative. When you do these number lines, you plug it in. If it's second derivative, plug it into the second derivative when you test it. Or first derivative, plug it in the first derivative. So if I plug in like 0, for example, I'd get a negative. If I plug in 2, I get a positive. So there is a point of inflection when x equals 1. Now this one says point of inflection. So I'm actually going to find the y value. So take your x value of 1 and plug it back into the original function up here to figure out your y value. That'd be 1 minus 3, -2, minus 9, -11, plus 7. So if I did my math right, it comes out to be -4. So at 1, -4, there is a point of inflection. So make sure you know how to do both of those. There'll be a lot of that on the test. You got to be able to first derivative, find relative max and mins, increasing, decreasing. Second derivative, points of inflection and concavity. All right, the last thing we're going to go over here is we're going to talk about the mean, oops, let me go back just a little bit, I'm sorry. We did that. Okay, last thing is the mean value theorem. This actually was in 4.3, so if you need to go back and review it, that's where you're going to look. And what we said is, if you have a function that's continuous and differentiable, so for example, this function is continuous and it's differentiable in that interval from a to b, if we find the average rate of change, we find AROC, there's some point in between there. What the mean value theorem tells us is if it's continuous and if it's differentiable on the interval, there's some point between a and b where the tangent line, the instant rate of change, will be exactly the same as the average rate of change. So what I'm thinking, this is the way I remember it right here, is as long as it meets the requirements, it's continuous and differentiable, then what I'm looking for is when does the average rate of change equal the instant rate of change. So remember, the average rate of change is like slope, right? We take the y minus y over x minus x. The instant rate of change is our derivative. So when does the average rate of change, the slope of the secant line, equal the instant rate of change equal the derivative? And then they'll a lot of times they'll ask you to find the c value on that. So let's find one. Let's do a problem where they do the mean value theorem on the review here. So if we look at number, all three of these would work here. These are all mean value theorems. So the first part is, does it apply? The second of all, if it applies, find the c value. Let's do 14. So let's check to see if it applies first of all. So there's two conditions. Is it continuous? So this function is not continuous at 3, right? If I plug 3 in, I get a 0 on the bottom. But 3 is not on my interval. So it is continuous from 4 to 6. So it is continuous. So if I were answering this question, I would say first, continuous on interval. Right, that checks off. It's continuous on the interval. The second thing is it differentiable? So let's find the derivative. Sorry, I'm going to change it. That's a terrible color, isn't it? Let me try. So derivative of f of x, I got to do the quotient rule. So I take the bottom, x minus 3, times the derivative of the top, which is 1, minus the top, which is x, times the derivative of the bottom, which is 1, all over the bottom squared. So if I do that, I say on top I get x minus 3 minus x, so I'd end up with negative 3 over. So there's my derivative right there. There's f prime. So let's see. When is the derivative undefined? So it has to be differentiable over the interval. So is there any places between 4 and 6 where the derivative doesn't exist? Well, the only time the derivative doesn't exist is at 3 again. So that's okay because we're looking from 4 to 6. So it's also differentiable. So is it differentiable? And yes, we check that off. So those are your two things. Continuous, yes. Differentiable, yes. So if it does it guarantee it on the interval? Yes. If it applies, find the c value. So now we're actually going to find the c value. So when you go to find the c value, what should pop in our head is I want to find out when does the AROC, the average rate of change, equal the IROC, the instant rate of change. Let's start with AROC. So let's find the average rate of change from 4 to 6. So I plug 4 in there, find your 2 points. If I plug 4 back in here, I get 4 over 4 minus 3 is 1. So I get 4, I think I get 4, 4 there. That's my point. I plug 6 in. I get 6 over, on the bottom I get 6 minus 3, which is 3. 6 over 3 is 2. So there's my point. So find the average rate of change. We go y minus y, 4 minus 2, which is 2, over 4 minus 6, which is negative 2. So the average rate of change comes out to be negative 1. We want to find out when does that equal the instant rate of change. The instant rate of change is given by the derivative. So when does the derivative, for what x values is the derivative equal negative 1? So if I can solve that equation, I have my c value. So let's go ahead and do that. I'm going to times the x minus 3 squared over on the other side. So we end up with negative 1 equals 3. Divide by negative 1. And I'm just looking back here. I almost forgot about this negative 3. This should be a negative 3 right there. Okay, now I divide by negative 1. So x minus 3 squared, if I divide it by negative 1, would be 3. You can take the square root of both sides. So x minus 3 equals plus or minus the square root of 3. Add the 3 over. So x equals 3 plus or minus the square root of 3. Okay, when I look at that, that means there's two answers. I have 3 plus the square root of 3. So there's two possible answers. And I have 3 minus the square root of 3. I need to find the one that fits between 4 and 6. 3 minus the square root of 3 is not going to be, it's going to be less than 4. 3 plus the square root. So that's my answer right there. It's going to be 3 plus the square root of 3. So that's what c equals. That is the c value when the instant rate of change equals the average rate of change. When the slope of the secant line, the line that goes through the 4, 6, through x is 4 and x is 6, that goes through these 2 points right here, when that slope of that line is equal to the slope of the curve, the instantaneous slope. Hopefully that helps. I know that's quick. It's hard. We can't review everything here. There's just not enough time. But what you can do is go back on each of those sections. If you get stuck on something or something doesn't make sense, look back at the assignment, pick some problems, try them again. Also be aware that the tests are cumulative. Like we've been doing all those derivative rules before this, so you're going to see some problems where you just have to take the derivative. You have to remember all those derivatives rules also. So try to find some time to review that. Hopefully this is helpful. Thanks, guys.